Now, the reason we're having this briefing is because in early October, the Jason-3 satellite will take over from Jason-2 as the reference mission for global sea surface height measurements, and it will be carrying on a time series that's been going on now for over 23 years. It's an incredibly important satellite, and in the next half hour, we want to tell the story of why Jason-3 is so important. And to do this, we've gathered speakers from all the partners involved in the Jason program. So to do some introductions, on my far left, I have Richard Gilmore from the European Commission's DG GROW Copernicus unit.
Hello, Neil. Hello. Good afternoon to the audience, both here in Darmstadt and following us on the internet.
And next to me, I have François Parisot, who's Jason-3 project manager at EUMETSAT.
Thank you, Neil. Good afternoon, everybody.
And on my right, I have Philippe Escudier, who's the oceanography program manager at the French space agency CNES.
Thank you, Neil, and good afternoon.
And on my far right, I have Pierre-Yves he's science director at Mercator Ocean.
Thank you, Neil, and good afternoon to all of you.
Okay. And we will also have, dialing in remotely, we will have Laury Miller, who's the Jason-3 program scientist at the National Oceanographic and Atmospheric Administration in the US. And we'll also have a recorded presentation from Willis from NASA-JPL. He's the Jason-3 project scientist. And the format for this briefing is that we'll have 6 short presentations, and then after that, we'll open the floor up to questions from the audience, and then also over Twitter. And we'd like people to use the hashtag AskJason3. So if we start with the first presentation, our first speaker is Richard Gilmore, and he's going to be talking about why the Jason-3 satellite is so important for the European Union's Copernicus Earth observation program.
Thank you, Neil, for the introduction. And I would also like to thank the hosts, EUMETSAT, for giving the European Commission the opportunity to speak at this Jason-3 briefing event. As you already said, Neil, in my short introduction, I hope to explain why Jason-3 is so important for Europe, and in particular for Europe's Earth observation program, Copernicus. I know the other presenters will focus on the technical specifics of Jason-3, so my presentation will describe in broad terms the Copernicus program and where altimetry and Jason-3 fits in with this. Now, some have described Copernicus as the most ambitious Earth observation program to date. It is a 7-year program running from 2014 to 2021 with an overall budget of €4.3 million. It involves the building, launch, and operation of close to 20 Earth observation satellites and the processing of the extensive data produced by these satellites into information that is useful for decision makers. It is a comprehensive system for monitoring the state of the environment, and it took almost 2 decades of European investment and sustained research and development activities to make the Copernicus program become an operational reality with sustained European funding. It is a truly European endeavor built on a pooling of European resources, but it is also a truly global endeavor in that it covers the entire globe and also builds on the contributions beyond Europe. We can schematically divide Copernicus into 2 main components, the space component and the service component. So let's start by looking at the space component of Copernicus. Although Copernicus is building its own dedicated space infrastructure, and more about that in just a moment, in the first stages, it will rely on numerous existing European and international space assets, the so-called contributing missions, which you can see on this slide. There are currently some 14 missions that contribute to the Copernicus program, for the most part European missions. Jason-3 fits into this landscape of contributing missions and is one of 2 altimetry missions along with Cryosat. But I would say that Jason-3 can be considered to be something of a special case, and this for a number of reasons. Firstly, it is the only mission based on international cooperation between Europe and the US, in particular between the main stakeholders, EUMETSAT, CNES, NOAA, and NASA. A sign, I would say, of the global importance of altimetry. Furthermore, it is the only contributing mission to receive Copernicus funding for part of the satellite's operations, a further indication of how important Jason-3 is to Copernicus. Another important aspect is that Jason-3 is part of a long-term project to ensure continuity up to 2030. And last but not least, as the reference mission, it is considered to be the European backbone of an altimeter constellation. For all these reasons, Jason-3 can be considered to be of central importance to the Copernicus program. But as I just said, Copernicus is also building its own dedicated satellites, the Sentinels. You can see on the slide the schedule for almost 20 satellites to be launched over a period of 13 years, ensuring continuity of observations through to 2030. There are 6 main families of Sentinels based on a wide range of sensing technologies to serve different Earth observation needs. So far, 4 satellites have been successfully launched: 1A, 2A, 3A, and more recently, 1B. In the context of today's briefing on Jason-3, I would like to focus on 2 Sentinel families, and you can see in the slide that I have highlighted these with the red rectangle. Firstly, Sentinel-3 is of particular interest. It is the first Sentinel to include an ocean topography mission with radar altimetry. It will directly rely on Jason-3 to calibrate its measurements. Secondly, I would like to draw your attention to Sentinel-6, a high-precision radar altimetry mission. In fact, Sentinel-6 is the name given to Jason-CS in the context of the Copernicus program. Jason-CS, or Sentinel-6A, is the reference altimetry mission foreseen to take over from Jason-3 around 2020. We can see from these first 2 slides, what we can see from these first 2 slides is that the Jason program will actually become an integral part of the Copernicus program. The short-term aim is to have a constellation of 2 Sentinel radar altimeters and a Sentinel reference mission to calibrate these. Now, we've seen in broad terms the space component of the Copernicus program and why Jason-3 is a central element to this. I'd like to complete the picture by saying a few words about the Copernicus services, and again understand why Jason-3 is important. Now, we might consider the space component and the Sentinels to be the eyes and ears of the Copernicus program, looking down at the Earth and gathering all kinds of information about the environment. If that is the case, then we can consider the services to be the brain of the program, effectively transforming the huge quantities of data from the space component into information that we can actually use. Information that allows us to understand the environment and take decisions. These services are structured into 6 main areas, covering all parts and all aspects of the Earth's environment. As far as Jason-3 is concerned, its altimetry measurements are of specific importance to the Marine Service, as the measurement of the height of the sea surface is an essential input parameter. I'd like to therefore briefly describe the Marine Service and the information that it provides. The Marine Service provides information and forecasts on the state of the ocean, including physical aspects such as ocean currents, sea temperature, sea ice cover, sea level, and salinity, but also other aspects such as biochemistry. It covers the entire globe and also offers more precise and tailored information for 5 European regional seas. It provides information that can be useful for a whole range of maritime activities. Just to give one example, that of shipping, where, for example, ships could use the information from the Marine Service to plan the most efficient routes as a function of the currents. One of the most important inputs from Earth observation is the measurement of sea height, which is essential for ensuring the accuracy of the forecasts. Jason-3 directly contributes to the quality and the accuracy of the Copernicus Marine Service forecasts by providing high-precision altimetry measurement. It further contributes by calibrating other altimetry measurements from other satellites, such as Jason-2, CryoSat-2, and of course Sentinel-3A, but also other international missions such as HY-2A and Altica. So to conclude, I hope that I've been successful in explaining why Jason-3 is so important for the Copernicus program. In short, I think that we can say that Jason-3 is an essential part of the ocean forecasting part of Copernicus. Thank you for your attention.
Okay, thanks, Richard. That's great. So now we're going to move on to François Parisot, who's going to talk to us about what happens when Jason-3 takes over from Jason-2, and also about what happens after Jason-3 comes to the end of its working life.
Thank you, Neil. So let me first explain you a bit why we are here today and what will happen with our 2 satellites, Jason-2 and Jason-3, in the coming weeks. So Jason-3 was launched on the 17th of January 2016, and a few weeks after its launch, it was placed, as you can see on this slide, on the same exact orbit at an altitude of 1,336 kilometers, very close to Jason-2. The distance between the 2 satellites is about 500 kilometers, representing only 80 seconds of time difference. So why do we do this? In 80 seconds, the ocean has not moved, nothing has changed in the ocean, and almost nothing has changed in the atmosphere. So this configuration allows to cross-calibrate very precisely and directly both systems. Check that the performance, that the new satellites are at least as good as those of its predecessor. This takes a bit of time because you have to remember that we want to measure the sea elevation with an accuracy of a few centimeters, again from an orbit of 1,336 kilometers. So you must recognize that it requires to accumulate a number of measurements and to look at all instrument and satellite performances to do this precise cross-calibration. So it has taken, as expected, a bit more than 6 months to perform this activity. Now, we have demonstrated that the Jason-3 performance are excellent, and it's now time for Jason-3 to take over from the old Jason-2. I say old because Jason-2 was launched in 2008, so has now accumulated more than 8 years of excellent service, significantly exceeding its nominal lifetime. But despite his age, Jason-2 is still in very good shape and ready to continue to deliver high accuracy sea topographic data. So in order to take advantage of this situation, to a brand new Jason-3 satellite and a still healthy Jason-2, we have entered into discussion with our users to see how best we can benefit from the 2 satellites. And the result of this discussion is that Jason-2 will be moved, as you will see on this, still being on the same orbit, but making ocean observation at different time and place than Jason-2. thus improving the overall coverage. This move necessitates a number of maneuvers using the propulsion system of the satellite. It will start on the 2nd of October and be completed by the 14th of October. At this time, and as illustrated here, instead of one single satellite track or measurement path, we will have two tracks, the second one being exactly in the middle of the first one. This configuration allows a better and more accurate detection of sea states, particularly in the area of high dynamics, such as the Gulf Stream, as you can see on these slides. Eddies locations and intensity are much better depicted with this new configuration. As was said before, the Jason satellites are not the only altimetry satellite today flying. We also have Sentinel-3, launched in February 2016. Sentinel-3 is also flying on a different orbit, and again, as illustrated here, the two satellites' ground track are different and complementary, allowing to maximize the coverage. Both missions are now operated here at EUMETSAT under the Copernicus umbrella and delivering key inputs, data feeding the marine environmental services. In 2017, Sentinel-B will join this fleet of altimetry mission. This allows to fulfill the user requirements that have expressed the need of one reference complemented by 3 complementary altimetry missions so as to get the adequate sampling of the ocean. As you will see in the presentation to come, almost 25 years of uninterrupted flow have now been accumulated. But 25 years is nothing when we address climate changes. So the crucial point now is to ensure continuity of service. And as was said before, this is the main objective of Jason-CS or Sentinel-6, the next reference altimetry mission, which is developed jointly by EUMETSAT, ESA, NASA, and NOAA with the support of CNES. The Sentinel-6 mission is implemented through 2 satellites, the first one being launched in 2020, the second one in 2025. And this will ensure the continuation of this, again, uninterrupted data flow up until 2030 or hopefully later on. Thank you for your attention.
Okay, thanks, François. Now we're going to look at the history of the Jason satellites with Philippe Escudier.
Thank you, Neil. The first thing I would like to address is to come back on this very essential role that altimetry is playing in ocean monitoring. This role is related to the fact that any change in the physics of the ocean change the elevation in the water. If you take an example, if it is stored in the ocean, it changes the temperature, and then through dilatation, the density of the water is changing, and then the elevation of the water is going up, is increasing. If on other topic, if currents are flowing in the ocean, it impacts the surface of the water due to the equilibrium of forces within the ocean, so that any current in the ocean will look like a slope on the ocean. And this is what is depicted on this figure, which shows the status of the ocean at the beginning of the first mission of this series of reference altimetry mission. It was TOPEX Poseidon, launched in 1992. And several weeks after the launch, we could get this picture, which shows the low and high of the ocean topography, and which can be read as the figure of the currents, large currents in the ocean. Actually, currents are flowing around the low and high of the ocean topography exactly the same way winds are blowing around the low and high of the atmospheric pressure. So this is an equivalent for oceanography of the well-known role of barometric pressure for meteorology. So from this short presentation, you can see that it's really important because either at surface or at depth, any change in the physics of the ocean can be measured through this integrated information provided by the altimetric measurement. As it was already said, an important point for this measurement is the accuracy of the measurement, because all those signals, change in temperature, currents, etc., turns into a signal which amplitude, in average, is about 10 centimeters. So to provide valuable information, we need to measure the altimetry, the elevation of the surface, with an accuracy which is better than 10 centimeters. And to do that, we need to combine a set of information to get the adequate measurements. There are more than 50 different steps in the computation of the surface elevation. To illustrate this, the criticality of this issue, this chart shows the progress that have been made that were necessary to reach this accuracy in one of those steps, which is the computation of the altitude of the satellite, which is the first step of this computation. Before the time of this, beginning of this reference altimetry mission, what we could do at this time was to compute an orbit with an accuracy that was was not reaching the meter accuracy. And it's only with this TOPEX Poseidon mission that the accuracy of this orbit computation was better than 10 centimeters. And you can see on this chart that after, thanks to research and development effort, both on the instrument and on the computation, now we are at a level of accuracy consistent with our mission objective. And this is one example of the multiple computation and that needs to be made to get this altimetric information. In parallel with this accuracy issue, a second one, which already was addressed, is the fact that due to the turbulent nature of the ocean, we need a good coverage both in space and in time. We need to revisit the global Earth every 10 days or so, and to get resolution which is compatible with the size of the EDs we want to monitor. And for that, as François mentioned, we need 4 satellites. So this was demonstrated at the beginning of this new era of altimetry by combining TOPEX Poseidon information with ERS information, and then this concept has developed, and now we have set up a requirement for a virtual altimetry constellation, which is now fully in place with Jason-3 complementing Sentinel-3 information. And beyond this constellation, which is now the basis for operational monitoring of the ocean, we are now making research and development effort to build new generation of altimetry instruments and satellites, because the user demand, which is already satisfied with the present service, is asking us to reach higher resolution both in terms of spatial resolution and time resolution. That's why we are working on new generation of instruments that will be tested with the SWOT demonstration mission, which will be in 2020, and that will eventually be useful to define future Copernicus step of the program beyond 2020. And this will be discussed later. Thank you for...
Okay, thanks, Philippe. Now we'll go to Pierre-Yves, who's going to tell us a bit more about how Jason-3 data are used in the Copernicus Marine Environment Monitoring Service.
Thank you. Okay, so I will now turn to the use and the role of Jason-3 for the Copernicus Marine Service. So the Copernicus Marine Service is one of the 6 services as part of the Copernicus program, as presented by Richard at the start of this discussion. It is implemented by Mercator Ocean under a delegation agreement with the European Union. So the Copernicus Marine Service is a major undertaking at EU level to provide an operational marine service. It's really building or more than 10 years on research and development at European level, in particular through the MyOcean project. So it is operational, it's scientifically assessed. It's covering both observations, so satellite, in situ, and models. And models are mandatory if you want to provide forecast of the state of the ocean. So models are used to provide reanalysis over the last 30 years, analysis and forecast. We are covering physics, so sea level, currents, temperature, salinity, sea ice, and also biogeochemistry. We are working with a network of European producers, which are coordinated by Mercator Ocean. So we have more than 50 marine centers all around Europe that are contributing to this operational system. We have a unique catalog. We have covering both the global ocean and all European regional seas. And we have a central information system to provide access to the different data. A major importance is also the service desk that we are running, which is used to support users for accessing all the data sets. So the service is generic. We call it a core service. And really the initial idea is that we need to have this core information on the ocean, which is available, readily available, open and free. And then you could develop, operational downstream application and have a network of users. And this initial idea actually was, the realization was quite a success, because as of today, we have more than 7,000 users, subscribers of the service that are using our products to a wide range of applications. We are actually covering 4 main areas of benefits, and we are actually monitoring our users for the different areas of benefits. So they range for the coastal and marine environment, the marine resources, weather, seasonal forecasting, and climate, and maritime safety. So the role of the Jason-3 for the Copernicus Marine Service is fundamental. And this is actually related to the fact that altimetry is unique and fundamental for ocean analysis and forecasting. As was already explained, so sea level as measured by altimetry is an indirect measure of ocean current, but is also representative of the interior of the ocean, the density anomaly at the interior of the ocean. And this is the reason why it has really a huge impact for assimilating into ocean model to provide a full description of the ocean state on forecasting. In addition, it's also an all-weather and global instrument, so that is really a huge impact for ocean analysis and forecasting. So Jason-3 is the reference mission. It's fundamental because it is used to intercalibrate all the other altimeter missions that we need. And it's also essential to provide, together with in-situ data, the ocean monitoring, ocean climate monitoring that the Copernicus Marine Service is providing. For instance, monitoring these large climatic events such as La Niña, El Niña, the mean sea level rise, and so on. This is part of the activity of the Copernicus Marine Service. But many of our applications require a high-resolution description and forecast of the ocean state. We have, for instance, dealing with applications such as prediction of the fate of marine pollution, ship routing, search and rescue, supporting the offshore industry, and all these applications that require a high-resolution description of ocean current and forecast. And for this, you need several altimeters. We need at least 4 altimeters, and Jason-3 needs to be complemented by other altimeter mission. And so there is really a critical importance and complementarity with Sentinel 3A and 3B from the Copernicus, but also the future Interleaved tandem mission of Jason-2. So, our concluding word, first, important to state here that Jason-3 is now fully integrated in the Copernicus Marine Service. So it's it became last week our reference mission. So it's part of our observation products through our sea level thematic assembly center, and it's also already used in the global and regional modeling and forecasting centers. As explained, since Jason-3 is essential for modeling and forecasting, we have a large proportion of the products that we provide today that are positively impacted by Jason-3. Actually, almost 60% of our products are impacted by Jason-3. There was a very smooth transition from Jason-2, so we were able to switch from Jason-2 to Jason-3 very smoothly. And that, I mean, it's important here to thank all the Jason-3 project team for their very hard work, making sure that Jason-3 and Jason-2 are fully consistent, and then they can be really used for operational monitoring. Last point is, as we are dealing with users, they need to have confidence that we will be able to provide a long-term service. So continuity is essential for us. On the fact that we have no decision to have this JSON-CS Sentinel-6 mission to ensure continuity of this essential measurement is really a major step forward for us. On final words, that Jason-3 needs to be complemented by other altimeters. This is mandatory to describe and forecast ocean current at fine scale. We know that we need at least 4 altimeters. We know that we have even more challenging task to describe at finer scale the ocean, and the SWOT mission will be the next breakthrough in oceanography. But this is very important to have this complementarity of Jason-3 with the other altimeters. Thank you.
Okay, thanks, Pierre. Next, we're going to go to a recorded presentation from Josh Willis from NASA-JPL, and he's going to be telling us a bit more about how Jason-3 data is used for climate monitoring.
This is a really important occasion for Jason-3 because it's the handoff from Jason-2 to Jason-3 of our climate record. The global record of sea level rise has been measured since the time of Topex Poseidon, starting in the early 1990s. It was handed off to Jason-1, followed by Jason-2, and now Jason-3. These missions measure globally average sea level rise, among a whole lot of other things. And that's important because the rising oceans are one of the most important indicators we have of human-caused climate change. In this graphic, you can see the rise in carbon dioxide over the last 50 or so years. This is caused by the burning of fossil fuels and is the major driver of climate change today. On the right, you can see one of the most important impacts of this change, which is the rising oceans. This measurement, which goes back to the Topex Poseidon days, shows how sea levels have risen globally in the last 23 years. Almost 8 centimeters of increase have been seen during this time, and all of that is due to the warming of the planet, the melting of the ice sheets and glaciers, and the thermal expansion of the oceans. Because the oceans absorb over 90% of the heat trapped by greenhouse gases and collect the water of the melting glaciers and ice sheets, this represents one of our most powerful indicators of the footprint of human-caused climate change. As Jason-3 takes over the record of climate change from Jason-2, we mark this occasion with this press conference because it's a reminder that we have to continue to measure the planet's climate in the most accurate way possible. In the next graphic, we can see how sea level rise is one of the things that we really are not very good at predicting out into the future. Which path are we on? Are we looking at 1 or 2 feet of sea level rise in the next 100 years, or are we looking at 5 to 6 feet, a devastating amount that would affect hundreds of millions of people across the planet? The Jason missions allow us to measure this very accurately and document how sea level rise is occurring and how fast we're looking at it happening today. Because of this, these missions are really one of our most important tools for monitoring the climate and its health. We look to these satellites in the future to continue measuring sea level rise out for another 5 or 6 years for Jason-3 until the launch of the Jason-CS missions in 2020 and 2025. I'm Josh Willis. I'm sorry I couldn't be there, but I'm really excited about Jason-3 and all the excellent data it's providing about the oceans and our changing climate.
Okay, and now we're going to our last speaker, which is Laury Miller from NOAA over in the US, and he's going to be joining us live via Skype.
Hi, I'm glad. Oops.
Okay, can you hear us okay, Laury?
Yeah, I have to kill my Safari. Okay.
Okay.
No feedback. Okay, thank you. I'm glad to be here. It's too bad that Josh is someplace in Greenland helping measure the changes in the ice of Greenland. Let me just bring to your attention a couple of what I think are important applications that NOAA, the National Oceanic and Atmospheric Administration, is using altimetry data for. And I think this brings to light the fact that Jason-3 and its predecessor missions have been incredibly versatile, not only for climate purposes, but also for near real-time applications. And one example that I'd like to give you is the impact of altimetry on tracking oil spills. And I have an image which shows the Deepwater Horizon oil spill, which occurred a couple of years ago. And it shows the oil being spread across the Gulf of Mexico. And superimposed on that is an image of the currents of the ocean, which are determined using a numerical model that is initialized with altimetry data. As Philippe explained, the currents of the ocean are controlled by the surface pressure of the ocean, the highs and lows that the altimeter can map. This is directly analogous to the way that meteorologists are able to determine the winds in the atmosphere by knowing the atmospheric pressure. But here we're using the surface of the ocean to talk about the pressure of the ocean. And it's information like this that's really extraordinarily useful in a near real-time application for making sure that the oil spill is contained or to give warning of it spreading to land. Information like this is also used by NOAA and the US Coast Guard to help devise search and rescue plans. If there's a disabled ship or if an airplane crashes and there are people in the water, we want to know where they're going to drift to. And the surface information, the sea level currents, derived currents from the altimetry, are used in a near real-time plan for devising a search pattern. Now, another example which may surprise you is the application of satellite altimetry and the Jason-3 measurements for the forecasting of hurricanes, one of the most difficult meteorological forecasting problems. We do a pretty good job of figuring out where hurricanes are going to go, but we have a lot of trouble precisely identifying when a hurricane is going to intensify. And so, for example, the example of Katrina, which hit New Orleans and caused a lot of devastation there. And as it turned out, that the intensification of hurricanes is controlled in large measure by the heat content of the ocean. The hurricanes feed off of the heat energy in the ocean. And the altimeter actually does a pretty good job of identifying those areas where there's a lot of extra heat, because that's where the surface of the ocean bulges up. And Katrina is actually an excellent example where the altimeter was able to identify a region that helped amplify the intensity of the hurricane. And finally, I'd like to mention something that probably has been mentioned in passing. We use the altimetry data from Jason-3 to help monitor and forecast the evolution of El Nino events, which are shown here in a video dramatizing the most recent El Nino, which occurred as a very large surface elevation spanning all the way from the west coast of South America, practically across the ocean. Now, the altimeter sees this very clearly as an elevated area of sea level, and being able to track the evolution of El Nino events allows meteorologists to forecast disturbances that will affect North American weather. The presence of an El Nino often disturbs the track of the jet stream, which in turn determines whether some areas of the US are going to get more rainfall or less rainfall, and even if there's going to be a drought in some areas. And in some cases, we can even tell when tornadoes, which are actually very difficult to forecast, where the tracks of tornadoes will be displaced. So these are three examples of what we at NOAA use the altimeter data from Jason-3 in near real time for forecasting purposes that are vital in terms of protecting lives and property. And so it's for this reason that we're extremely excited by the fact that Jason-3 is now about to become the reference mission. So that's what I wanted to convey to you today. Thank you.
Okay, thanks, Laury. That's brilliant. That should stimulate a lot of questions as well. So thank you for joining us. Okay, now we've come to the end of the presentation. So what we'd like to do is take a couple of questions from the audience, and then we'll have a look at the questions that have been coming in on Twitter. So does anyone have any questions here?
Thank you for the nice presentation. It's a question, actually, I'm not sure to whom of the speaker I have to ask this question. It's about the applications this altimetry, Jason, and in general, altimetry satellites. A lot of applications were mentioned, but what about tsunamis, especially the tsunami we had a few years ago in Japan? My question is how these altimetry satellites are able to analyze data from the tsunamis and maybe to warn also a population. Mm-hmm. Thank you.
Who'd like to take that one with that?
Well, maybe I can answer on this. I mean, using altimetry to predict a tsunami is not possible because you need really need to observe the tsunami with very high space and time resolution. So it's not possible. You will need a huge number of altimeters. Still, we can observe a tsunami with altimetry, and there were several, very nice studies showing the observation of the tsunami because we had, by chance, a track was crossing the tsunami. So we can get information on the structure of the tsunami when it is at sea, but it's more offline analysis and so on. But prediction of the tsunami with altimetry, it's not something which is possible.
Okay. Does anyone else have a question they'd like to ask the panel? Nope. Okay.
How many users did you have for Jason-3?
François?
I think this was already mentioned, for instance, for the
so we have the user as part of the Copernicus Marine Service, so that user of all the products that we have. As I explained, many of these products are dependent on Jason-3, but not only, because we are also providing satellite observation of sea surface temperature on model and so on. But today, as part of the Copernicus Marine Service, we have more than 7,500 subscribers, which are the people who are connected to our system. And every year, more than 4,000 users that connect to our system and download data. So this is really increasing year after year. So this is really the sign that what I explained, that the initial idea is that we have to provide open and free data for the ocean, and then that we help the development of application is actually a success.
Okay, so maybe now if we move over to our Twitter questions, I think we should be able to see what's been coming in on the screen down here. Okay, so we have the first question is from Peter de Selding. Hi, Peter. Is there any way of estimating the remaining useful life of Jason-2? Maybe.
Thanks for the question. So first, I want to say that Jason-2, as I mentioned, is still very healthy. So we have not had any significant failure of Jason-2. So we are still on the primary chain. You know that most of the elements of the satellite are redundant, and we are on the primary chain for for all elements. So we have reserved of fuels on board the satellite. So we can hope that Jason-2 will last as long as its predecessor, Jason-1, which reached a lifetime of 11 years, if I'm correct. So we all cross our fingers to get the same lifetime for Jason-2.
Mm-hmm. Okay, let's have a look at the next question then. Okay, so we have a question from Dr. Mark Higgins, and he's saying he gets asked a lot, why do we have multiple satellites measuring sea surface height, and how is it possible to measure the seafloor with altimeters? So who would like to take that one?
Okay, I can start at least for the first part. As I explained, I mean, we need multiple satellites to measure the sea level variations. It's simply because the ocean is really a turbulent system, so it's full of meanders, eddies, filaments. So current like the Gulf Stream is not at all a quiet river, so it has a very small scale feature, so typically at the level of 100 kilometers. So if you want to observe these signals, those eddies, which are very important for many applications, you need to have several altimeters, at least 4. I mean, that's why we request to have a sufficiently accurate representation of the sea level and ocean current, and also to be able to predict them. Okay, so second one is on the seafloor, so it's totally different topic, but it's going back to the principle of altimetry measurements. So the main measure of the altimetry is the sum of the geoid, which is the equipotential of the Earth's gravity field, on the sea level or dynamic topography, which is a signal of interest for oceanographer. If you look at the level of the geoid, at small scales, the geoid reflects the variation of mass in the interior of the ocean, so it can be used to derive ocean bathymetry. This is the reason why when you have, again, sufficient altimeter at fine scale, you can get very useful information on seafloor and bathymetry.
Okay, can we take the next question then? Okay, so Tim Hewson's asked, to understand the importance of continuity, how could a gap in the time series of ocean altimetry be handled? Who would like to take that one?
I can try first. I think that's the major impact is an accuracy of the series of data. If we have a gap, it will be much more difficult to intercalibrate the measurements provided by the new satellite with respect to the previous one. Mm-hmm. So the difficulty will be intercalibration, and we will have then to rely on in situ data to make this intercalibration, which may be not at the level of accuracy that we can do presently by overflying Jason-2 and Jason-3 on making measurements at the same time, same place, which allow very precise intercalibration.
Okay. Can we take another question then? Okay, so we have another question from Peter de Selding. You've explained Jason-3 and Sentinel continuity to 2030, but does this get you to 4 altimeters to that time or just 3?
Okay.
Who would like to respond on that one?
Yes, actually, those are the mainly the European contribution, plus of course the coordination with the US. But in practice, we are relying, as was explained by Philippe, on a virtual constellation. So it's not only this component, but we have also other missions. For instance, today we are using a Chinese satellite, HY2. We are using Altica, which is a Saral CNES India cooperation. So that's the whole idea of this virtual constellation, where we are gathering all the different inputs from different agencies.
Okay. We have a question from Viju John. How does information about sea level improve weather forecasting? So who would like to take that?
Laury is Laury
is Laury still on the line? No? Okay, perhaps if you
try
take
this, because this is really something on weather forecasting. is one example was given by Laury on this hurricane forecasting. And since you need to have information, through information of sea level, you have information of the heat content of the ocean, which is an important mechanism to feed the hurricane. So if you can measure the sea level from altimetry, you can improve the forecast of the year of an important weather event, which is hurricanes. Mm-hmm. But of course, then for the whole weather forecasting, it's one element among many others, but it's important observing system.
I think maybe
maybe to complement this answer, we may address at this time one point which we did not address before, which is that in addition to the sea surface topography, altimeters allow to make measurements of significant wave heights. So we are also measuring waves, which is a parameter which is at the interface between weather forecasting and ocean. But we are providing to the weather forecasting centers measurements of waves which are used for their forecast of waves.
Okay.
Globally speaking, I would say that now also as Pierre-Yves indicated, so altimetry help building ocean models, and now people are coupling the ocean model together with the atmospheric model so as to improve the weather forecast on mid to long term, giving trends on the weather forecast by coupling ocean and atmospheric models.
Okay. Okay, we have a question in from Marco Trovatello. Will Jason-3 help achieve the goals of COP21? So who would like to take that one?
I mean, the goals of COP21 depends a bit what are the goals of COP21. What we do with altimetry is make measurements. So we as was explained by Josh, the increase of mean sea level rise is again a key indicator of the global warming. So what we can do, I would say, is providing some evidence of this climate warming through the sea level rise
and quantitative evolution of this.
Yeah.
Okay. Ryan Laird has a question. To what order of magnitude can you measure the rise in sea level? How much can you relate to global warming and change of sea surface temperature?
For the order of magnitude of the accuracy, well, it depends on how you can do averages on elementary measurements. The basic measurements provided by Jason-3 is provided every second, which turns to be every 6 kilometers over the Earth. And these basic measurements has an accuracy of about 3 to 4 centimeters. So this is the elementary measurements. But when you are interested by the mean sea level rise, you can make averages of all these elementary measurements over 10 days, which is a repeat cycle of Jason. And then the level of accuracy you can get at the present time is half a millimeter per year.
Half a
So
millimeter.
you can imagine that this implies a lot of calibration and validation to be sure that making those averages, you really down the accuracy level down to that. But a lot of effort has been done, and now we can say that we are at the sub-millimeter levels for the mean sea level rise.
Okay. Okay.
And for second question?
Well, maybe a short comment on how much can you relate to global warming and change of SST. This was, I think, briefly presented by Joss, but that's something we can measure with complementary measurement. We have, for instance, this is also part of the data that we deliver through the Copernicus Marine Service, the Argo global array of profiling flows that measure temperature variation of the ocean. So we can quantify the part of sea level change which is due to the heating of the ocean, so the dilatation of the ocean. And today, it's slightly more than 1/3 of this expansion, which is due to expansion. And the remaining part of the sea level rise is due to the melting of ice sheet.
Okay. We have a question from SciTech, DW SciTech. How will the Jason-3 satellite give us more data on the Earth's sea levels? We've kind of covered in a way.
Yeah, I think we have already covered that one. Huh?
Do we have another? Okay, so we have another question. Why does the radar altimeter use pulses at 13.6 gigahertz in the Ku band and 5.3 in the C band to measure distance to sea? Maybe that's for you, Philippe.
Yeah, that's directly related to this issue of accuracy of the measurements. The radar which is used for the information, the signal travels through the atmosphere, and atmosphere interacts with the signal, and this is a perturbation that we have to take into account to get the adequate level of accuracy. And one of these perturbations is due to the ionosphere, which is the upper atmosphere effect, and to quantify this effect, we use these double frequency measurements, which allow us to quantify this effect and correct it in the measurements that we deliver to the users, final users.
Okay. We have a question from Tim Hewson. We saw the increase in sea level is uneven. Where's the greatest increase and the lowest? And do we know why? So who would like to take that one?
Okay,
maybe you, Pierre? Or, yeah.
Yes, we know. I mean, if on that, so the great value of altimetry is not only to give a global mean of global estimate of mean sea level variation, but we can look at the regional details. And when you use the data together with models, as we do in the Copernicus Marine Service, you really have the understanding of why you have all these differences. And if you look at a map, and it's difficult to give a simple answer to this question, because first it depends on time. If you look on average over 10 years, 20 years, or 30 years, it will not be the same. But what you see is simply the change in repartition of mass in the ocean due to the ocean circulation and wind. So this is well understood. And if you look at the local effect, it can be maybe 10 times more than the global average, but it will vary over time. So this is really due to the internal dynamics of the ocean, but one of the great value of altimetry together with the complementary measurement is to map these variations.
Okay. All right, well, I think we've got time for one more question on Twitter. So this is from Phil Nolan. Can you quantify the contribution of Jason satellites to weather forecast accuracy? Who would like to take this one?
I think
we already answered.
Yeah, it's a bit difficult, I think, maybe to quantify today the contribution of Jason satellite to weather forecast accuracy. Again, as I mentioned before, through the coupling of ocean and atmospheric model, it's helped improving the what we call the monthly weather forecast or the seasonal weather forecast. So trying to identify whether next summer or next winter will be colder or will be rainy or not. But it's a bit difficult to quantify it into the, I would say, a number of accurate days of forecast. This is the objectives with altimetry, except the point mentioned by Philippe related to the measurement of wave heights and things like that. But the objective of coupling this ocean and atmospheric model is rather to improve the mid-term to long-term weather forecast.
On Jason-3, on Jason-3 is an ocean mission. So we know we can quantify the large impact it has on ocean forecast accuracy. Yeah. You know that today, without any altimeter system, we cannot forecast ocean current. That's it. And we know very much how much altimeters are needed to improve the forecast and so on. But this is a forecast of the ocean.
Okay.
But I see that maybe an example to illustrate, not quantify, but to illustrate this, is the El Nino forecast. It's clear that using altimetry really improves our capacity to forecast several months in advance big events such as the El Nino.
Okay, well, I think we've come to the end of our time now for this briefing. So I apologize if we didn't get to all the questions that people had in on Twitter, but we've come to the end. We'll actually be putting this briefing on YouTube later in the week. So if you missed any of it, you'll be able to watch it on there later. Also, one thing I wanted to mention is if you have if this has gained your interest in ocean monitoring from space, we are actually organising a massive open online course monitoring the oceans from space, and that will start on October the 24th, and it will be, you can find out more details about it from our website. And so all it remains to say really is to thank you to all our speakers, and thank you everyone for being here, for the audience, and also thank everyone who's been watching this online, and have a good evening. Thanks.